Welcome to AP Calculus AB Units 3 through 8. This video covers every topic tested on the AP exam across these 6 units. Let's get started. Unit 3. Differentiation, Composite, Implicit, and Inverse Functions. Section 3.1. The Chain Rule. What is it and why do we need it? When one function is nested inside another. For example, sine of x squared. You cannot simply differentiate the outer function and stop there. You must also multiply by the derivative of the inner function. This is called the chain rule. It comes up constantly in calculus, both on its own and combined with every other rule, you know. Master it early and everything else becomes easier. The chain rule formula. If a of x equals f of g of x, h prime equals f prime of x times g prime of x. In Leibniz notation, d over dx equals d over d over dx. Read it like this: derivative of the outer evaluated at the inner times the derivative of the inner. The two forms say exactly the same thing. Use whichever feels more natural for the problem in front of you. Chain rule examples. Example 1. Find the derivative of sine of x squared. The outer function is sine of u, whose derivative is cosine of u, in is x squared, whose derivative is 2x. Multiply them together. The answer is cosine of x squared times 2x. Example 2. Find the derivative of the quantity 3 hakims plus 1 raised to the 5th power. The outer function is u to the 5th, whose derivative is 5 witters to the 4th. The inner function is 3 ims plus 1, whose derivative is 3. Multiply them. The answer is 5 times the quantity 3 ims plus 1 to the 4th 3, which simplifies to 15 times the quantity times plus 1 to the 4th. Find the derivative of to the power 5x. The outer function is e to the u, whose derivative is e to the u. The inner is 5x, whose derivative is 5. The answer is 5 times e to the 5x. Always identify the outer and inner functions before you start differentiating. Section 3.2. Derivatives and exponentials. These 6 rules are non-negotiable. Commit them to memory. The derivative of e to the x is e to the x. The derivative of a to the x is a to the x times the natural log of a. The derivative of the natural log of x is 1 over x. The derivative of log base of x is 1 over x times the natural log of a. The derivative of the natural log of u, using the chain rule, is u prime over u. The derivative of e to the u using the chain rule is e to the u times u prime. The last 2 forms with the chain rule are the ones you will use most often on the AP exam. Section 3.3. Implicit differentiation. When it cannot be isolated in terms of x, we use implicit differentiation. Differentiate both sides of the equation with respect to x. Treat e as a function of x. Apply the chain rule to every I term. The derivative of I to the n is n times to the n minus 1 times d over dx. Then collect all d over dx terms on one side and solve for d over dx. The key rule to remember is d over dx of I equals n times to the n minus 1 times d over dx. That extra factor of d over dx appears every single time you differentiate a I term. Implicit differentiation worked example. Find d over dx for the equation x squared plus I squared equals 25. Step 1. Differentiate both sides. Plus I times d over dx equals 0. Step. Isolate the d over dx terms. 2i times d over dx equals negative 2x. Step 3. Solve. D over dx equals negative a over I. Warning: apply the chain rule to every I term every single time. Never skip it. Section 3.4. Derivatives of inverse functions. If f and f inverse are inverse functions, then the derivative of f inverse at x equals 1 divided f prime of f inverse of x. The strategy to find this is straightforward. To find the derivative of f inverse at a, step 1, find c such that f of c equals a. Step 2, the answer is 1 divided by f prime of c. This formula always works, but you need to evaluate f prime at the right point. Inverse trig derivatives. These formulas appear constantly on the AP exam. Know all 5 of them. The derivative of arcsin of x is 1 over the square root of 1 minus x squared. The derivative of arccos of x is negative 1 over the square root of 1 minus x squared. The derivative of arctan of x is 1 over 1 plus x squared. The derivative of arcsin of u with the chain rule is u prime over the square root of 1 minus u squared. The derivative of arctan of u with the chain rule is u prime over 1 plus u squared. Notice that arcos is simply the negative of the arcsin derivative. Unit 4. Contextual applications of differentiation. Section 4.1. Motion along a line. If s of t is the position of an object at time t, then differentiation gives us the motion quantities. Velocity v of t equals s prime of t. It is the rate of change of position. Acceleration of t equals v prime of t, which equals s double prime of t. It is the rate of change of velocity. Speed equals the absolute value of v of t. Speed is always non-negative. These three definitions are used in every single motion problem on the AP exam. Motion interpretations. When v of t is greater than 0, the object is moving in the positive direction. When v of t is less than 0, the object is moving in the negative direction. When v of t equals 0, the object is momentarily at rest. When of t is greater than 0, velocity is increasing. When of t is less than 0, velocity is decreasing. When velocity and acceleration have the same sign, the object is speeding up. When velocity and acceleration have opposite signs, the object is slowing down. The last two rows are especially important for speeding up and slowing down questions. Section 4.2. Linearization, also called local linear approximation. The tangent line to f at x equals approximates the curve near that point. The linearization formula is L of x equals f of a plus f prime of a times the quantity x minus a. Use it to approximate f of x for values of x close to a. Example. Approximate the square root of 4.02 using f of x equals the square root of x at a equals 4. F of 4 equals 2. F prime of x equals 1 over 2 times the square root of x. So f prime of 4 equals 1/4. L of x equals 2 plus 1/4 times the quantity x minus 4. L of 4.02 equals 2 plus 1/4 times 0.02, which equals 2055. The actual value is approximately 0, 0 or 99, so the approximation is very close. Section 4.3. Related rates. Two or more quantities change or time. Their rates of change are related through a geometric or physical equation. We differentiate that equation with respect to time t to connect the rates. The 5-step method is 1. Draw and label a diagram. 2. Identify all given rates and the unknown rate. 3. Write an equation relating the variables. 4. Differentiate both sides with respect to t. 5. Substitute known values and solve. Related rates, key equations. For a circle with area A equals pi r squared, dA over d equals 2 pi r times d/r over dt. For a sphere with volume V equals thirds pi r cubed, dV over dt equals 4 pi r squared times d/r over dt. For a cylinder with volume V equals pi r squared h with r fixed, dV over dt equals pi r squared times dA over dt. For the Pythagorean relationship squared plus b squared equals c squared. 2a time is da over dt plus 2b times db over dt equals 2c times dc over dt. Units matter. If r is in centimeters and t is in seconds, then dr over dt is in centimeters per second. Related rates, worked example. Problem. A circle's radius is growing at 3 centimeters per second. How fast is the area increasing when r equals 5 centimeters? A equals pi r squared. Differentiate. dA over dt equals 2 pi r times dr over d. Given information, dr over dt equals 3 and r equals 5. Substitute. dA over dt equals 2 pi times 5 times 3 equals 30 pi, which is approximately 94.2 square centimeters per second. Section 4.4. L'Hopital's rule. When direct substitution gives 0 over 0 or infinity over infinity, differentiate the numerator and denominator separately. The rule states, the limit as x approaches of f of x over g of x equals the limit as x approaches of f prime of x over g prime of x. Warning, check for an indeterminate form first. Never apply L'Hopital's rule blindly. Example 1. The limit as x approaches 0 of sine x. This gives 0 over 0. Apply L'Hopital, the limit of cos x over 1 evaluated at 0 equals 1. Example 2. the limit as x approaches infinity of x over e to the x. This gives infinity over infinity. Apply the of limit to the x as x goes to infinity equals 0. You can apply L'Hopital repeatedly if the result is still indeterminate. Unit 5. Analytical Applications of Differentiation. Section 5.1. Mean Value Theorem. Intuition. If a function is continuous and differentiable on an interval, somewhere on the instantaneous rate of change must equal the average rate of change over the entire interval. Here is a helpful analogy. If you averaged 60 miles per hour on a road trip, your speedometer must have roughly 60 miles per hour at some moment during that trip. The mean value theorem says the same thing mathematically. Mean value theorem statement. The hypotheses are: 1f is continuous on the closed interval of b. 2f is differentiable on the open interval of b. The conclusion is f prime of c equals f of b minus f of a divided by b minus a for some c in the open interval of b. Rolle's theorem is the special case where f of a equals f of b. In that case, there exists a c where f prime of c equals 0. The mean value theorem is often used on free response questions to justify the existence of a specific derivative value. Section 5.2 Extreme Value Theorem. If f is continuous on a closed interval of b, then f both absolute maximum on minimum on that interval. The extreme value theorem guarantees that extreme values exist. It does not tell you where they are. That requires additional work. Both conditions are required. The interval must be closed, not open, and the function must be continuous on that interval. The theorem fails if the interval is open or if f has a discontinuity. Section 5.3. Critical points. A critical point of f occurs where f prime of x equals 0 or where f prime of x is undefined. Prime equals 0 means a horizontal tangent line. F prime undefined means a corner, a cusp, or a vertical tangent. Critical points are candidates for local extrema. You must still test whether each one is actually a maximum, a minimum, or neither. First derivative test. Each critical point C, check the sign of f prime on both sides. If f prime changes from negative to positive, there is a local minimum at C. If f prime changes from positive to negative, there is a local maximum at C. If f prime does not change sign, there is neither a maximum nor a minimum. Also, f prime greater than 0 means f is increasing. F prime less than 0 means f is decreasing. Section 5.4. Second derivative test and concavity. F double prime greater than 0 means the function is concave up, shaped like a cup opening upward. F double prime less than 0 means the function is concave down, shaped like a cap opening downward. For the second derivative test, if f prime of c equals 0 and f double prime of c is greater than 0, then c is a local minimum. If f prime of c equals 0 and f double prime of c is less than 0, then c is a local maximum. An inflection point is where f double prime changes sign, where the concavity changes. Warning: f double prime of c equals 0 is inconclusive. Use the first derivative test instead. Section 5.5. Optimization problems. Optimization is finding the maximum or minimum value of a quantity. The 7-step process. 1. Read carefully and identify what to maximize or minimize. 2. Define variables and write the objective function. 3. Use a constraint to reduce to one variable. 4. Find critical points by setting the derivative equal to 0. 5. Use the first or second derivative test to confirm whether it is a max or min. 6. Check endpoints if the domain is a closed interval. 7. Answer the question with correct units. Always verify whether a critical point is a maximum or minimum. Never assume absolute extrema on a closed interval. Use the closed interval method, which is guaranteed by the extreme value theorem. Step 1. Find all critical points inside the open interval of B. Step 2. Evaluate f at each critical point. Step 3. Evaluate f at both endpoints f of a and f of b. Step 4. The largest value is the absolute maximum. Step 5. The smallest value is the absolute minimum. Always check the endpoints on a closed interval. Unit 6. integration and accumulation of change. Section 6.1. Antiderivatives. F is an antiderivative of f if f prime of x equals f of x. Because the derivative of any constant is zero, antiderivatives form a family. We write plus c to represent all of them. C is called the constant of integration. The notation for the indefinite integral is the integral of f(x) f of x plus c. The const c cannot be determined without additional information such as an initial condition. Basic integration rules. The power rule. The integral of x to the n dx equals x to the n plus 1 divided by n plus 1 plus c. This works for all n except -1. The natural exponential. The integral of e to the x dx equals e to the x plus c. The general exponential. The integral of a to the x dx equals a to the x divided by the natural log of a plus c. The reciprocal. The integral of 1 over x dx equals the natural log of the absolute value x plus c. Sine. The integral of sine x dx equals negative cosine x plus c cosine. The integral of cosine x dx equals sine x plus c. Each of these is the reverse of a differentiation rule. Section 6.2. Riemann sums. Approximating area. Divide the interval of b into n equal subintervals of width delta x, which equals b minus o over n. Sample a point in each subinterval. The sum of the rectangle areas is the sum from I equals 1 to n of xi star times delta x. There are 4 types. The left Riemann sum uses the left endpoint of each subinterval. The right Riemann sum uses the right endpoint. Midpoint rule uses the midpoint. The trapezoidal rule averages the left and right sums. As n goes to infinity, all Riemanns approach the exact definite integral. Trapezoidal rule. The trapezoidal rule approximates the definite integral using trapezoids and is more accurate than left or right sums for smooth functions. The formula is t sub n equals delta x over 2 times the quantity f of x0 plus 2 times f of x1, 2 times f of x2, and so on plus 2 times f of xn minus 1 plus fxn. The coefficients follow the pattern 1, 2, 2, 2, and so on 2, 1. The trapezoidal rule overestimates when f is concave up. It underestimates when f is concave down. Section 6.3. Fundamental theorem of calculus part 1. F of x equals the integral from a to x of f of t dt, then f prime of x equals f of x. The derivative of an accumulation function returns the original integrand. Basic form d over dx of the integral from a to x of f of t dt equals f of x. With the chain rule, when the upper limit is vex, d over dx of from a to d of x of f of t d dt equals f of g of x times g prime of x. D over dx of the integral from 1 to x cubed of sine t dt equals sine of x cubed times x squared. The upper limit is the variable. The lower limit is a constant. Section 6.4. Fundamental theorem of calculus part 2. This theorem lets us compute a definite integral exactly using any derivative f. The formula is the integral from a to b of f of x dx equals f of b minus f of a where f prime equals f. The procedure is 1. Find any antiderivative f of f. 2. Compute f of b minus f of a. The constant c cancels out. Example, the integral from 1 to 3 of x squared dx equals x cubed over 3 evaluated from 1 to 3 equals 27 over 3 minus 1 over 3 equals 26 over 3. Properties of definite integrals. The integral from a to a of f to dx equals 0. Same upper and lower limit gives 0. Reversing bounds. The integral from a to b of f to dx equals negative the integral from b to a. Linearity. The integral of c times f plus d times g dx equals c times the integral of f plus d times the integral of g. Additive intervals. The integral from a to b of f dx equals the integral from a to c plus the integral from c to b. Remember, net area equals the integral of f. Total area equals the integral of the absolute value of f, which requires splitting at the zeros of f. Section 6.5. U substitution. U substitution is the chain rule reversed. Use it when the integrand contains g of x and its derivative g prime of x. Step 1. Choose u equals g of x, usually the inner function. Step 2. Compute u equals g prime of x dx. Step 3. Rewrite the entire integral in terms of u. Step 4. Integrate with respect to u. Step 5. Substitute back u equals g of x. Example. The integral x times cosine x squared dx. Like x squared. Then do equals 2x dx. The integral becomes the integral of cosine u do which equals sine u plus c, which equals sine of x squared plus c. Unit 7. Differential equations. Section 7.1. Slope fields. Introduction. A slope field visualizes the ordinary differential equation di over dx equals f of xi. At each point xi in the plane, draw a short line segment with slope equal to f of xi. A solution curve is a curve that is tangent to the slope segments everywhere it passes through them. Different initial conditions give different solution curves, each one a valid solution to the differential equation. To sketch a slope field, evaluate di over dx at several key points and draw dashes at those slopes. Slope field example, di over dx equals x. Here you can see the slope field for di over dx equals x. The segments point up to the right and downward to the left, matching the slope value x at each point. The white and green curves are solution curves. They flow smoothly along the segments. These solutions are the family of parabolas e equals x squared over 2 plus c for different values of c. Section 7.2. Separation of variables. Use this method when di over dx equals g of x times h of I. The right side factors into a function of x times a function of I. The separated form is the integral of di over h of I equals the integral of g of x dx. The steps are 1. Separate variables, di on one side dx on the other. 2. Integrate both sides. 3. Add plus c on one side only. 4. Solve for I. 5. Apply the initial condition to find c. Warning. Add plus c before solving for I. Do not wait until after you exponentiate. Separation of variables. Worked example. Solve di over dx equals x times e given that I of 0 equals 2. Separate di over e equals x dx. Integrate both sides. Natural log of the absolute value of e equals x squared over 2 plus c. Exponentiate e equals a times e to the x squared over 2. Apply initial condition. E of 0 equals 2, a equals 2. The answer is e equals 2 times e to the x squared over 2. Section 7.3. Exponential growth and decay. The most common ODE on the AP exam is di over d equals k times I. The solution is e equals I0 times e to the k times t. When k is greater than 0, this is exponential growth. When k is less than 0, this is his exponential decay. Applications include population growth and decay, radioactive decay, and half-life continuously compounded interest, with formula A equals P times e to the R times T and Newton's law of cooling. Section 7.4. Logistic growth. When a population has a carrying capacity, L growth, as P approaches L. The logistic differentiation is dP over dt equals K times P times the quantity 1 minus P over L. Key facts. The population grows fastest when P equals L over 2, which is the inflection point of the solution curve. As P approaches L, the growth rate approaches 0. The solution is S-shaped, also called a sigmoidal curve. P is always positive if P of 0 is positive. Unit 8. Applications of integration. Section 8.1. Average value of a function. The average value of f on the interval of b is the constant height that gives the same area under the curve as the actual function. The formula is average equals 1 over the quantity b minus a times the integral from a to b of x dx. The mean value theorem for integrals says there exists c in the interval of b such that f of c equals the average value. The function actually attains its average value somewhere on the interval. Example. Find the average value of f of x equals x squared on the interval 0 to 3. F average equals 1/3 times the integral from 0 to 3 of x squared dx equals 1/3 times 27 over 3 equals 3. Section 8.2. Area between curves. Introduction. We want the area of the region trapped between two curves f of x and g of x from x equals a to x equals b. When f of x is greater than or equal to d of xx on the entire interval, the area is simply the integral of f minus g. We are integrating the vertical distance between the two curves, area between curves, formulas and steps, using vertical slices integrating with respect to x. A equals the integral from a to b of the quantity f of x minus g of x dx, where f is greater than or equal to g. Using horizontal slices integrating with respect to e. A equals the integral from c to d of the quantity r of e minus l of I die, where r is the right curve and l is the left curve. The steps are: 1. Set f of x equal to d of x to find the intersection bounds a and b. 2. Check which curve is on top in the interval of b. 3. Integrate the absolute value of f of x minus g of x. Warning: if the curves cross inside the interval, split the integral at each crossing point. Area between curves. Worked example. Find the area enclosed by I equals x squared and I equals x plus 2. Find intersections. X squared equals x plus 2, so x squared minus s minus 2 equals 0. The quantity x minus 2 times the quantity x plus 1 equals 0. The bounds are x equals -1 to x equals 2. Check which is on top. Equals x plus 2 is above e equals x squared on the interval -1 to 2. Set up the integral. Equals the integral from -1 to 2 of the quantity x plus 2 minus x squared dx. Evaluate. This equals x squared over 2 plus 2's facts minus x cubed over 3 evaluated from -1 to 2, which gives 9 over 2. Section 8.3. Volumes of revolution, disk method. Rotate the region around the x-axis. Each cross-section perpendicular to the x-axis is a full disk. The formula is v equals pi times the to b of the quantity f of x squared dx. The radius of each disk equals f of x, which is the height of the region above the x-axis. Example: rotate e equals the square root of x about the x-axis for x in 0 to 4. Equals pi times the integral from 0 to 4 of the square root of x squared dx. That simplifies to pi times the integral from 0 to 4 of x dx. That equals pi times x squared over 2 evaluated from 0 to 4, which equals 8 pi. Volumes of revolution, washer method. When the region does not touch the axis of rotation, each cross-section is a washer, a disk with a hole in the center. R is the outer radius farther from the axis. R is the inner radius closer to the axis. The formula is v equals pi times the integral from a to b of the quantity r of x squared minus r of x squared dx. Always identify which curve is farther from the axis. That is the outer radius r. If you are rotating about the line I equals k, instead of the x-axis, adjust r equals the absolute value of f of x minus k. Example: rotate the region between I equals the square root of x and I equals x about the x-axis for x in 0 to 1. V equals pi times the integral from 0 to 1 of the quantity square root of x squared minus x squared dx. That equals pi times the integral of x minus x squared dx, which equals pi over 6. Section 8.4. Volumes with known cross-sections. Some solids are not formed by rotation. Instead, cross-sections cut perpendicular to the x-axis have a known shape. The general formula is v equals the integral from a to b of a of x dx, where a of x is the area of the cross-section at position x. Common shapes: squares have area s squared. Equilateral triangles have area square root of 3 over 4 times s squared. Semicircles have area pi over 8 times s squared. Rectangles with height h have area s times h. The variable s is usually the width of the base region at position x, which equals f of x minus g of x. Final recap. AP Calculus, Units 3 through 8. Unit 3 covered. The chain rule, derivatives of logs and exponentials, implicit, differentiation, and inverse function and inverse trig derivatives. Unit 4 covered. Motion along a line with velocity and acceleration linearization related rates, and L'Hopital's rule. Unit 5 covered. The mean value, the extreme value theorem, critical points, the first and second derivative tests, concavity optimization, and absolute extrema. Unit 6 covered. Antiderivatives, the basic integration rules, Riemann sums, the trapezoidal rule, the fundamental theorem of calculus parts 1 and 2, integral properties and U substitution. Units covered. Slope fields separation of variables exponential growth and decay and logistic growth. Unit 8 covered. Average value of a function area between curves the disk and washer methods for volumes of revolution and volumes with known cross-sections. That is everything from units 3 through 8. Good luck on the AP exam.